What you're looking at is the end of a legacy and the violent birth of a giant. Think this is just senseless destruction? Think again. To build the world's most powerful nuclear reactors and supercars, we must first return to the void. This is the brutal, high-tech starting point of the billion-dollar heavy machinery cycle. Meet the Hamel V B950, a mechanical predator designed for one thing: absolute shredding. It doesn't care about the history of these vehicles. Its twin shafts, rotating with bone-crushing torque, fold entire steel frames like they're made of wet paper. This is raw, unyielding power, turning tons of automotive history into manageable scrap in mere seconds. Notice the engine blocks. Even the densest cast iron is treated like candy. The intelligent hydraulic sensors are the brain behind the brawn, detecting resistance and reversing instantly to ensure the feeding never stops. It's a rhythmic, terrifying dance of steel versus steel, where only the strongest survive. As the fragments fall onto the discharge conveyor, they leave behind their past. These jagged pieces are destined for the furnace, where 1,000-degree baptism will erase their identity. Steel never dies. It only waits for its next evolution, something far bigger, tougher, and more dangerous than a car. But how does this pile of jagged metal become the backbone of a nuclear plant? The furnace is calling. Prepare yourself. We're about to step into the heart of the inferno.
1 second of distraction and the floor becomes a river of fire. Before we witness the rebirth of steel, you must see this. In the world of heavy industry, there is zero room for error. Look at this pot line, a single misaligned crane hook, a sudden jolt, and hundreds of liters of molten metal overflow. This isn't just a technical fail, it's a terrifying reminder. When you're dealing with thousands of degrees, the factory floor can turn into lava in a heartbeat. Precision isn't a choice, it's the only thing keeping these workers alive. Now, imagine trying to tame this heat and multiplying the pressure by 1,000.
What you're looking at is the end of a legacy and the violent birth of a giant. Forget everything you know about strength. You are now standing beneath 13,000 tons of absolute authority. At Sheffield Forge Masters, this press doesn't just shape metal, it tames it. Imagine the weight of 20-kilo-class submarines pressing down on a single point. This is where steel meets its master.
As the heat intensifies, we move to the heart of the Forgetal Group. Here, the atmosphere shifts from raw power to a high-tech robotic symphony. You are witnessing a synchronized dance of fire and silicon. Look at the precision. Massive robotic arms handle glowing, multi-ton billets with the grace of a ballet dancer, yet with a grip that could crush a skyscraper. These components are heated to a staggering 1,200 degrees Celsius, a point where steel is pliable enough to be shaped, but dangerous enough to vaporize anything it touches. In this facility, every strike of the hydraulic hammer and every micro-rotation of the lathe is monitored in real time by an army of sensors. This isn't just forging, it's molecular engineering on a grand scale. After the forge, the heavy-duty CNC machines take over. Watch as they carve through hardened, heat-treated steel as if it were soft butter. Every shaving of metal that falls is a step closer to perfection. In this world, precision is measured in microns, 1,000th of a millimeter. A single error, a tiny deviation, and $1 million component becomes nothing more than high-grade scrap. But at Forgetal, perfection is the only standard they accept.
But for the ultimate transformation, we must look to the east. Welcome to the Bohai Steel Group in China. Prepare yourself, because what you are about to see defies the typical limits of metallurgy. How do you take an 18-ton solid block of glowing steel and turn it into a perfect 10-meter wide ring in under 10 minutes? The answer lies in this: the radial axial ring rolling machine, a masterpiece of modern physics and mechanical brute force. Watch the transition closely. It begins as a thick, white-hot donut of steel, fresh from the furnace, radiating a heat that would be unbearable to the naked eye. But as the massive rollers engage, the transformation is breathtaking. The physics at play here are staggering. Two massive conical rollers press against the walls from the inside and outside, while two others control the vertical height, stretching the metal simultaneously from every direction. In exactly 567 seconds, the diameter expands from a few meters to over 10 meters wide. It's like watching a giant incandescent halo being born from fire. But don't let the speed or the massive scale fool you. This isn't just about getting bigger. It's about maintaining structural perfection under extreme stress. Throughout the entire expansion, high-speed laser sensors and ultrasonic monitors track the wall thickness and roundness to extreme levels of accuracy. The grain structure of the steel is being forced to flow in a continuous circular pattern, giving the ring a strength that no welded joint could ever match. Why is this level of precision necessary? Because these rings are the literal backbone of our future infrastructure. They will become the main support flanges for massive offshore wind turbines, standing tall against hurricane-force winds, or the critical containment rings for the next generation of nuclear reactors. These components must withstand decades of immense pressure and corrosive salt air without a single microscopic crack. A failure here is not an option. Every revolution of the machine, every millimeter of expansion is a calculated victory over the stubborn nature of metal. In this hall, we see the limits of what is possible being pushed further than ever before. Seeing 18 tons of solid steel shaped with such terrifying efficiency is a testament to human ingenuity. We have taken the raw, chaotic elements of the Earth, and through the absolute power of heat and pressure, we have forged them into the indestructible bones of a new civilization. This is what happens when we stop dreaming and start building at the edge of the impossible. The 10-meter halo is complete, a silent guardian of the power that will soon run through it. We now move from the giants of industry to a guardian that sits silently in your own home, a vessel that must never ever fail. Liquid petroleum gas, or LPG. To most, it's just a metal cylinder under the stove, but to an engineer, it is a high-pressure bomb, tamed by science. The manufacturing process of an LPG cylinder is a masterclass in safety-first engineering. It begins with deep drawing. Watch as massive hydraulic presses take a flat disc of steel and stretch it into a seamless dome. This isn't just about shaping, it's about ensuring the metal grain remains uniform. Any thinning of the wall, even by a fraction of a millimeter, could lead to a catastrophic rupture. But the real magic and the real danger lies in the welding. The two halves of the cylinder are joined using automated submerged arc welding. This creates a bond that is actually stronger than the steel itself. But how can we be sure? In this facility, trust is replaced by verification. Once the two domes are fused, the cylinder moves to the grinding and polishing station. Here, high-speed abrasive wheels strip away the excess welding bead, smoothing the seam until it is nearly invisible to the touch. This isn't just for aesthetics. Any sharp edge or protrusion could become a stress point, a tiny flaw where rust might start its slow, destructive work. Next, the steel shell enters the automated spray booth. It is here the cylinder receives its first skin, a high-durability, anti-corrosion powder coating. Charged with static electricity, the paint particles cling to every curve, creating a seamless, airtight barrier. This vibrant coat is then baked in a massive oven at high temperatures, curing into a hard, protective armor that will survive years of rough handling and outdoor exposure. Finally, before it can be trusted with the energy within, the precision brass valve is installed. This is the cylinder's heartbeat, the only gatekeeper of the pressure inside. Massive torque-controlled machines screw the valve into the neck with calibrated force, ensuring a metal-to-metal seal that is absolute. Only now, fully dressed and armored, is the cylinder ready for its final judgment.
Every single cylinder must pass through the trial by water. Submerged in deep tanks, they are pressurized far beyond anything they will ever encounter in your kitchen. We look for the smallest bubble, a single microscopic leak that would mean immediate rejection. Then comes the ultimate test, the burst test. One cylinder from every batch is pushed to its absolute limit until it literally rips apart. Engineers study the way the metal tears. It must fail in a specific, predictable way. This steel skin is what stands between your family and the immense energy stored inside. From the heat treatment furnace that relieves internal stress to the final powder coating that prevents corrosion, every step is a silent promise. A promise that when you turn that valve, you are met with power, not peril.
The first task involves feeding large steel coils into the slitting line, where the sheet is carefully cut into strips tailored for each pipe diameter. It's almost unbelievable how neatly the raw steel transforms under these massive rollers. These strips then enter the ERW welding machines, forming continuous hollow profiles, while electric resistance welding seals each seam. After welding, the pipes pass through a straightening section, correcting any slight deformations and ensuring dimensional accuracy. That straightening process looks deceptively simple but controls steel with impressive force. The next action uses high-speed automatic saws to cut pipes to precise lengths, ready for inspection. Quality control specialists measure wall thickness, outer diameter, and weld consistency. Seeing these checks in real time feels like watching the steel's personality being evaluated. Some pipes may then proceed to galvanizing or other surface treatments depending on client requirements, adding corrosion resistance and extended durability. Once surface treatments are complete, pipes are bundled and labeled for shipment. The organization here is fascinating. Each bundle is prepared to survive global logistics intact. Packaging teams secure the pipes so they can reach construction sites and factories worldwide without damage. With a monthly capacity of approximately 27,000 metric tons, Basatli Boru Profil balances scale and quality, producing domestic, industrial, and structural pipes efficiently. You'd never guess that these continuous lines handle such huge volumes, yet maintain consistent quality. Finally, finished profiles are stacked and loaded for transport, demonstrating the seamless coordination of human skill and advanced machinery. The precision of these combined operations is quietly awe-inspiring. Every component from coil to shipped pipe reflects a blend of tradition, technology, and careful oversight. Somehow, the plant makes it all look almost effortless. Operators guide machines, materials flow, and each step builds on the last, producing steel pipes that will form buildings, infrastructure, and industrial equipment around the world. Galvanized C-profiles roll through win-win machinarias forming lines, shaped for roofing and dry construction frameworks. Machines guide each sheet as it bends and compresses to precise angles. The metal slides through like it's following a path it already knows. Finished profiles are stacked, ready to reinforce structures efficiently. Simple mechanics, but serious strength at work. Engineers and machines at Berlik Makina Sanvetik, Limited STI. Shape steel pipes from EU51 to 127 millimeters at speeds up to 90 meters per minute. The ERW pipeline aligns raw material, feeds it into the high-frequency welding unit, then cuts and stacks finished pipes with precision. Optional roll leveling and profile cutting lines enhance output. Didn't expect the weld seam to stay that clean at such speed. Staff monitors every stage, adjusting parameters to maintain quality. That pipe stack grows faster than you'd think, almost like the machine never tires. Efficiency and control define this line. Operators at the workshop handle 20 millimeters thick metal sheets with expertise, turning them into collar components efficiently. Sheets are first aligned carefully for the hydraulic folding presses, making sure each one is positioned accurately. Hydraulic presses apply consistent pressure to bend the metal evenly across the entire sheet. The folding operation continues with precision, forming the required angles for each collar. Operators monitor every press cycle and adjust the machinery if needed. Support jigs hold sheets firmly during each press, preventing misalignment. After folding, each collar is visually inspected for angle accuracy and uniformity. Edges are refined, and any minor irregularities are corrected, preparing components for further assembly. This stage emphasizes the importance of skilled handling combined with precision machines. Even thick metal sheets are transformed into functional, durable collars. Maintaining consistent quality while handling heavy sheets showcases the teamwork between machinery and operators. Strong steel 09G2S is pushed into the helical forming machine, shaped into a D600 screw flight with a 219 millimeters inner diameter. The plate enters the dies and is driven through a tightening arc that lifts one side and compresses the other to reach the 380 millimeters pitch. The force this machine applies feels unreal for a 20 millimeter slab. Each rotation forms the right-hand direction uniformly. That bend looks like the metal finally decided to cooperate. The machine keeps pressure steady until the full flight is completed. Workers weld and assemble flatbed semi-trailers, each movement combining strength and skill. Flatbed semi-trailers, especially the 40 feet 3-axle models, are assembled to carry containers, construction materials, agricultural goods, and machinery. Every completed flatbed ensures safe transport of heavy and varied loads. Steel and complex machinery converge at Atomenergomasch's plant in Russia to form the core of Kudankulam nuclear power plant's steam generators. The plant's cranes handle components that weigh several tons, moving them with surprising agility. The facility produces components for all Russian-designed nuclear reactors, currently under construction worldwide. Raw steel plates, pipes, and tubes are sorted and stored with precise identification for each assembly sequence. Workers check each steel plate for imperfections before it enters the production line. The weight of these plates makes the forming presses seem like instruments of raw power. Cutting, bending, and rolling lines take over as plates become shaped tube sheets and manifolds. Every machine is calibrated daily to maintain alignment within strict tolerances. Specialized machines bend large diameter pipes while robotic welding arms join assemblies with remarkable consistency. The weld seams are visually inspected as the robot pauses, confirming accuracy before proceeding. It's oddly satisfying how each tube bundle slides perfectly into the drum, almost like they were designed to fit on the first try. Primary and secondary circuits are assembled within the generator casing. Engineers constantly measure tolerances to ensure welds, flanges, and connections comply with nuclear standards. Technicians also mark each connection to track assembly progress systematically. Modules are then subjected to hydraulic pressure tests, ultrasonic inspections, and leak checks. The hydraulic test pressures look like they could challenge the unit more than expected, yet everything holds flawlessly. Finally, every verified steam generator is staged for shipment, combining the heft of heavy industry with precise engineering. The horizontal lathe shapes enormous propeller shafts for giant ships. Operators guide a 15-meter section of a direct-driven propeller shaft through the horizontal lathe at axle fibro. The machine handles extremely large ship components efficiently. This setup handles immense metal pieces with surprising control. Centrifugal casting dies up to 36 feet long and 5 feet in diameter are moved into position. Cranes place dies with pinpoint accuracy. Unbelievable scale for critical defense and industrial components. Operators maneuver long machine parts with Cymex systems, hauling beams into sea containers efficiently. That lift looks way stronger than a normal forklift could handle. Seeing beams spread weight evenly makes complex loads feel simple. Thousands of meters of copper wire are wound daily by the WHDF 1000 with perfect consistency. Operators feed spool wire carefully, aligning it for uniform winding across the drum. Each wire layer is guided through multiple pulleys to maintain perfect alignment, ensuring consistency. Wire tension is monitored constantly to prevent slack or overstretching, ensuring every layer is consistent. The drum rotates steadily while the carriage moves laterally, forming each turn exactly where it belongs. Supervisors check alignment indicators throughout, preventing misplacement of wire strands. Regular calibration of the tension sensors keeps the winding process stable. Automatic sensors pause the machine instantly if deviations are detected, protecting both material and equipment. As wire layers build up, operators adjust speed and carriage travel to maintain tight tolerances. Guides and pulleys direct the wire smoothly, avoiding abrasion or kinks. The machine handles high-current copper wire, and its precision ensures conductivity is uncompromised. Even minor misalignment could affect coil performance, so constant observation is essential. After winding, the coil is secured and inspected for uniformity. Each coil is measured for diameter and roundness before moving to testing, guaranteeing dimensional accuracy. The combination of automated mechanisms and skilled oversight maximizes throughput without compromising quality. Maintenance crews regularly check bearings, pulleys, and spools, keeping downtime minimal and reliability high. The workflow highlights the synergy between human skill and mechanical precision, with each action critical to final product performance. Integrated diagnostics record process parameters, enabling optimization for future production runs. Winding patterns vary depending on application, and operators select the correct program accordingly. Training ensures that both seasoned technicians and new operators maintain standards consistently. Occasionally, supervisors perform random checks on finished coils to ensure specifications are met. Final visual inspection confirms coil integrity before dispatch. Seeing such a high-speed winding operation executed flawlessly is striking. The coordination between operator, sensors, and machine underlines the depth of industrial engineering expertise. Every component, from spool to drum, contributes to the final efficiency and quality of the coils. Attention to these small adjustments keeps production both reliable and high quality. This setup proves the importance of precise process control in delivering reliable, high-performance wire products. How does the MCS-TB1621 build each tire with perfect layer alignment? The MCS-TB1621 tire building machine assembles motorcycle and three-wheeler tires from 16 inches to 21. Operators watch the layers of rubber, cords, and beads align seamlessly. Raw materials are fed onto the machine, then positioned and shaped into the tire carcass with precision. The coordination between rollers and belts keeps everything moving smoothly. The machine completes each tire quickly, maintaining uniformity and quality across the production line. Even complex tire designs are handled without hesitation. From roughing to finishing, the MU500VA completes complex parts faster than traditional methods. The trunnion table and 5-axis control allow multi-sided operations in a single chucking. You can't help but marvel at how smoothly it handles complex geometries. Aluminum impellers are machined at 500 minutes, with feed rates of 500 millimeters per minute, roughing each slot in 30 minutes. Cast iron turret housings undergo ID turning at 300 meters per minute, producing precise internal diameters in 22 minutes per cycle. Tool changes with the optional matrix magazine make workflow almost effortless. Mirror plates crafted from A5052 receive 5-axis milling, ensuring tight tolerances. Chain magazines and trunnion motion maintain consistent quality across parts. Even threads are cut with surprising autonomy, Operators monitor processes while automation handles positioning flawlessly. The combination of axes, spindles, and control ensures repeatable precision. From roughing to finishing, the MU500VA completes complex components efficiently. The craftsmanship of Nakamura Tome combines with advanced AI and IoT to redefine multitasking machining. The WT1502 handles bar diameters up to 51 mm and processing diameters up to 190 mm at high spindle speeds. The twin-spindle upper and lower turret configuration allows simultaneous machining with multiple tools, combining several processes in one setup and cutting down machining time dramatically. This innovative approach enables operators to handle complex geometries without repeatedly repositioning the workpiece, making production smoother and faster than expected. The machine's design allows for high-speed milling while keeping tool wear minimal. Raw bar stock is first loaded onto the machine using bar feeders or automated gantry loaders. Automated loading reduces human error and ensures consistent positioning. Automation ensures each bar is positioned consistently for precise machining. Twin turrets then engage the workpiece with milling power of 5.5 kilowatts on the upper and 3.7 kilowatts on the lower turrets, spinning at 6,000 minutes. This step reduces the need for multiple setups while maintaining high accuracy, keeping productivity high. Some operations also exploit the upper y-axis with a 70 mm stroke to reach intricate contours. The combination of multiple spindles and turrets allows simultaneous cutting on different points, saving significant time. Even detailed helical contours can be produced in one operation. As machining continues, precision is maintained by the NT SmartX control unit, designed for fast and accurate operation. IoT software, NT SmartSign, and the AI-powered NT Thermo Navigator continuously monitor thermal displacement and optimize process parameters. These systems reduce errors and maintain consistency across production batches. These systems enhance consistency across each cylinder or component produced, ensuring tolerances that match industrial requirements. Operators can track multiple parameters at once thanks to the integrated control systems. Operators can monitor the workpiece while shot blasting or surface finishing begins, providing protective layers and preparing components for painting or further treatments. The finishing line smooths surfaces to meet industrial specifications. Surface treatments are consistent, reducing post-processing corrections. Automated processes reduce manual handling, minimizing chances for mistakes. Throughout this process, the WT1502's multitasking capability reduces production cycles dramatically. Operators can complete more cylinders per shift with fewer setups. Components move from rough machining to finishing without unnecessary downtime, demonstrating a continuous flow that surprises even experienced technicians. The integration of multiple tools, spindles, and turrets within a single machine allows Basatli BORU Profil ASH to maintain high throughput while keeping quality uncompromised. The machine adapts easily to different cylinder types without requiring manual adjustment. Didn't expect the machine to handle multiple operations at once like this. Even the most complex designs are machined with repeatable accuracy. The precision of simultaneous cuts looks like controlled chaos turned into productivity. Even complex shapes are processed with confidence and speed. That coordination of turrets and spindles almost looks like a synchronized performance of steel and electronics. The machine's AI optimization helps maintain consistency even during long production runs. From initial loading to final finishing, each step is designed to maximize efficiency and maintain product integrity. The combination of advanced controls, IoT, and AI ensures a reliable and predictable production process. The WT1502's capabilities showcase the potential of multitasking CNC machining for high-demand industrial applications. The colossal 120,000 pounds generator is carefully positioned on a 9-axle trailer, requiring a second driver for the tail end, a testament to its immense weight. Every wheel and axle is calculated to support the load safely. Cranes move in perfect coordination, guided by expert hands, as the rotor is detached from the stator without shifting the generator. It's wild to see such a massive rotor lifted with apparent ease, watching these experts manage the generator. Every adjustment matters. The operation flows seamlessly despite the scale involved. Safety and precision dominate the scene. From forging to flight test, each bevel gear vertical shafts for the EC225 undergoes a rigorous sequence of machining, inspection, and assembly. Operators handle forged blanks carefully, placing them on turning machines to achieve exact dimensions. Machinists ensure each blank is aligned before any cutting, reducing imbalance later. Turning smooths surfaces, preparing the gear for teeth carving. Gear cutting follows, with specialized cutters creating teeth that match strict specifications. Operators monitor feed and rotation, keeping tolerances consistent. The cutting stage is critical to prevent future wear or misalignment, highlighting the importance of operator oversight. Nitriding strengthens the gear surfaces, increasing durability under extreme loads. Spiral bevel gear grinding refines tooth geometry, ensuring smooth engagement with mating components. Electron beam welding joins components that must resist high stresses. Non-destructive testing begins with ultrasonic inspections, detecting internal flaws. Radiographic testing provides a secondary check for hidden defects. NIT water quenching stabilizes the metallurgical structure, followed by magnetic particle inspection to reveal surface cracks. These inspection steps are essential for long-term reliability, giving operators confidence in every part. Superfinishing removes microscopic irregularities, creating uniform surface roughness. Runout inspection verifies axial alignment, while surface roughness inspection ensures friction and contact meet design requirements. The 3D measuring machine maps component geometry, confirming all tolerances. Gearbox assembly integrates the vertical shaft with other components, with operators coordinating each fit precisely. Rig testing evaluates the functional performance under simulated conditions. Main rotor hub assembly connects the shaft to the helicopter's rotor system. Coordinated teamwork between operators and machinery is key at every assembly stage, ensuring minimal errors. Flight tests validate operational readiness, confirming that each bevel gear vertical shaft meets Eurocopter's high standards. The combination of traditional craftsmanship and modern technology ensures reliability in EC225 operations. Seeing these stages handled with such exacting standards underscores the engineering expertise involved. The workflow highlights the direct link between material treatment, process control, and final performance. Every step, from forged blanks to flight-ready shafts, demonstrates the critical precision necessary in aerospace manufacturing. Even small deviations here could affect helicopter performance, making careful adherence to each process vital. Step into the daily operations of La Sisa Trasporti Industriali SRL, a logistics powerhouse operating across 10 sites with 400 specialized vehicles. The fleet moves millions of tons each year using modern machinery and skilled operators. Forklifts handle loads from 2 to 52 tons, equipped for specific handling tasks. Industrial tractors tow trailers up to 300 tons. That pull is seriously something. Roll trailers and semi-trailers transport up to 120 tons, while self-propelled vehicles manage pallets efficiently. Reach stackers lift cargo up to 45 tons, integrating smart control systems. Loaders with magnets or grabs complete complex loading sequences. Operators track and identify materials, ensuring seamless storage and retrieval. The yard management system integrates all machinery digitally, optimizing movements. Maintenance coverage is comprehensive, keeping all vehicles in peak condition. Operators must love that reliability. Each shift combines human expertise and mechanical strength to move semi-finished and finished products reliably. From dumper operations to rubber shovel loaders, each vehicle plays a precise role. Observing the variety of machines at work highlights the coordination required to maintain safety and speed. The combination of reach stackers, tractors, and forklifts demonstrates La Sisa's ability to handle highly diverse logistics tasks. Didn't expect this many different machines working together. Some equipment may appear oversized for a single pallet, yet it completes the task effortlessly. Digital systems monitor each movement, keeping operations synchronized. Even the largest trailers move smoothly thanks to expert operators. These people know their stuff. La Sisa exemplifies industrial logistics mastery with 20 million tons handled annually. The workflow shows how advanced equipment and operator skill merge seamlessly. Passengers experience smoother rides as trains traverse the improved Kettering-Corby line. Digital signals and upgraded bridges enhance reliability. 21 kilometers of track, 4 kilometers drainage, and 73 kilometers cabling ensure smooth operations. Finally, speed limits lifted. Operators and machinery work together to turn aluminum into high-quality pot sheets. Sheets that already have their basic pot shape move to the finishing line at Aluminium Metal Industries Belfangedi. Each sheet passes through a visual inspection before cutting. Cutting machines trim each sheet to exact specifications, removing any excess material. Operators watch closely and intervene. The combination of automated machines and skilled operators ensures efficiency without sacrificing quality. Finished sheets are checked before stacking. Never thought these thick aluminum forms could end up so sleek and precise. This stage proves the critical role of careful machining in producing durable, high-quality pots. Specialized grinders refine the edges for uniformity. Edges are then smoothed and burrs removed, turning rough metal into safe, functional surfaces. A simple edge could make or break the pot, yet the team handles it like pros. Deep inside Samisa's sprawling industrial site, the manufacturing heartbeat of heavy-duty machinery never pauses. Raw steel arrives in large billets and is routed straight to the forging sector, where hydraulic presses reshape the metal into early preforms. The opening phase moves fast, with operators coordinating each billet's position under the press. That press force feels heavier than its frame suggests. Those preforms transition into Samisa's machining bays, where CNC mills and heavy lathes contour shafts, hubs, and structural parts. Each machine runs in tight sequence to keep production steady. Kind of surprising how quickly the chips pile up beside the CNC table. Finished pieces are sent to the welding shop. Teams assemble frames, support arms, and large housings using MIG and TIG welders. Heat distortion is managed by clamping rigs while parts come together. That moment the arc grabs onto the metal always feels like a power move. Once welded modules are complete, they enter surface preparation. Shot blasting clear scale, then painting booths coat every module with primer and epoxy layers. After curing, components move to hydraulic test benches, where pressure cycles confirm structural endurance. Certified assemblies then head to storage, ready for shipment. Experience the variety of aluminium profiles produced daily at INVEST Lieutenant in Italy, from micro-profiles to heavy-duty structural sections. Each billet carries the potential to become dozens of different profile types, a true testament to engineering versatility. The sheer volume of around 50,000 tons per year highlights the industrial scale of the operation. Heated billets move into the extrusion press, aligned carefully for consistent output. The press forces aluminium through custom dies, producing hundreds of section types. From tiny 25 grams per meter profiles to massive 20 kilograms per meter sections. It's surprising how the same press handles both the smallest microprofile and the largest structural profile with ease. After extrusion, profiles slide along the runout table where operators cut them to precise lengths. Cutting speed and accuracy must be perfectly synchronized to avoid waste. Aging ovens treat the profiles with exact heat cycles to enhance mechanical strength and dimensional stability. The thermal treatment stage shows the subtle interplay of temperature and time in achieving perfect material properties. Profiles exiting the ovens are significantly stronger, prepared for structural and architectural use. Mechanical testing stations confirm the profiles meet the strictest strength requirements. Digital measurement stations verify dimensions to microns, ensuring quality across all profiles. Operators can adjust the process in real time if measurements are outside tolerance. The combination of skilled operators and digital scanning technology ensures uniformity throughout the line. Profiles are then sorted, bundled, and readied for transport. Warehouse coordination ensures that production flow is uninterrupted from line to truck. Workflow efficiency is impressive, as multiple profiles are handled simultaneously without error. The plant's layout optimizes both speed and operator safety. Some of the smallest extrusions seem almost delicate next to the heavier structural profiles, highlighting aluminium's versatility. The variety of profiles allows for applications from lightweight frames to heavy structural beams. This mix of light and heavy profiles demonstrates the precision and engineering behind each extrusion. Each profile type goes through a rigorous inspection before leaving the plant. The plant produces thousands of profiles daily, reflecting deep technical expertise and strict process control. The extrusion line shows that industrial efficiency and product flexibility can coexist. Even at high volumes, quality is never compromised, proving the robustness of the system. High-speed metal shaping unfolds at Repcon with rotary hot swaging machines. Rotary hot swaging machines shape each piece with impressive speed and consistency. Heated workpieces are aligned and fed into the swaging system, where strokes compress the metal precisely. Operators monitor diameter, length, and wall thickness throughout the process. Induction heating ensures the metal reaches optimal malleability for shaping. Up to 10,000 strokes per minute achieve uniform neck formation on each part. Finished pieces are checked for tolerance and surface quality before proceeding. The blend of thermal control and mechanical precision keeps production efficient. Powerful presses at the forging plant shape thick steel billets into precise, compact forms through the upset forging process. Each steel billet is first heated in a furnace before being carefully positioned into the hydraulic press for forging. Operators align each billet meticulously, applying force to expand and shorten the steel in controlled stages. That press packs more punch than you'd think for its size. Heated billets glow bright as they are compressed repeatedly, forming durable components for automotive and industrial applications. High-strength axle shafts depend on steel that can take extreme loads, and Parsons' heavy-duty forging line shows how each step drives that durability. Billets are heated until they reach forming temperature, and the forging press drives them through stage dies to shape the core profile. That first hit always reminds you how much force these machines control. A worker guides each piece through the die set, and the part's outline grows with every stroke. On the next station, the preform is reheated and placed beneath a larger press that sets the final axle shaft geometry. A trimming unit removes excess flash, leaving a clean perimeter. The hot shaft moves to controlled cooling, keeping its structure stable for machining. In Parsons' machining plant, lathes cut the bearing seats and milling units finish the spline ends. A measurement step verifies alignment and straightness before the shaft moves to surface treatment. The glowing part looked like a giant metal torch, and the comparison fits the heat of the process. A cast steel valve strong enough to hold pressure is shaped inside sand molds that are destroyed right after a single use. Sand casting defines the valve body first, using compacted molds to create the outer structure. Molten steel is poured into these cavities, filling every space before solidifying into a rough casting. Those molds collapse and disappear, yet the metal they shaped remains as a rigid barrier against pressure. The outer form is fixed at this stage, long before any cutting tool touches the surface. For smaller and more complex internal components, lost wax casting is used. Wax patterns are coated with ceramic layers, then heated so the wax drains away, leaving precise cavities. Molten steel fills these spaces, forming parts that guide flow and sealing inside the cast steel valve. What looks like a single solid object later actually comes from multiple separately formed pieces. Each internal path is locked in place once the metal fills these narrow cavities. The molds move into a push furnace where temperature rises to around 800 degrees Celsius and is maintained for nearly 2 hours. This stage stabilizes the metal structure and removes residues left from earlier processes. Internal strength develops here in ways that cannot be judged by surface appearance alone. Changes at this stage influence how the valve resists pressure over long operating periods. After cooling, machining defines threads, sealing faces, and connection points. Cutting tools remove excess material and refine each dimension so components fit accurately. Internal mechanisms such as gate, globe, or check elements are then installed into the valve body, completing the functional system. Alignment between these parts determines how the valve opens and closes under load. Final inspection tests sealing performance under pressure conditions. The finished cast steel valve operates as a controlled barrier, regulating flow without leakage. From loose molten metal and temporary molds, it becomes a fixed control point, capable of resisting constant internal force.
Blades that will sit underwater end up dictating how an entire power station performs, even though each piece begins as separate steel segments waiting to be joined inside the Francis turbine. Large steel plates are cut and shaped into curved sections that will later form the runner blades, with alignment checked repeatedly to keep every angle consistent. Sections are positioned and welded into larger assemblies, gradually revealing the circular runner structure that defines the Francis turbine's core. That curved steel suddenly starts looking like something that can control a river. Heavy machining refines each surface after welding, removing excess material and bringing critical dimensions into tolerance so the runner can rotate smoothly under load. The hub is prepared and matched with the blades, ensuring each connection distributes force evenly once the turbine operates under water pressure. There's a moment where the whole structure looks too heavy to ever move, then you remember water will drive it. Assembly continues with careful fitting of components, including guide vanes and surrounding structures that control how water enters and exits the runner. Each part is aligned to maintain balanced flow, which directly affects efficiency and long-term operation. Final checks verify that the Francis turbine can handle continuous rotation, pressure changes, and mechanical stress without deviation.
Once fully assembled, the Francis turbine stands as a complete system, ready to convert water energy into mechanical motion, linking every fabricated piece into a single controlled function. All that steel ends up responding to nothing more than moving water, which feels almost unfair.